All right, group 5 with the resolved dust.
So, hi everyone, we are here to present the project number 5, the spatially resolved dust properties in nearby galaxy, supervised by Frederic and Lara, and made by a lot of collaborators. So for this presentation, we are going to present you 2 main scientific goals, also the data and the method we use, and the result we obtain after 1 week of very hard work. So for the scientific goal, we have 2 main goals. So the first one was to learn how to homogenize images of galaxies at multi-wavelengths and to build spectral energy distribution. And these goals can be useful to estimate the dust-to-gas mass ratio, to have a better understanding of the heating source, and also to have to study properties of dust in order to gain information on dust evolution. So just to say, the 2 main goals were made by all of us. We didn't share the work, or at least we tried to do all of the work.
So the targets that we analyzed were 2 nearby galaxies, NGC 3938 and NGC 1140, which are located in the local universe. And so we wanted to explore the dust properties in these 2 targets. And we used for this the Dustpedia archive, which is a catalog that consists of observations from the UV to the millimeter. It is very useful because it hosts a lot of nearby galaxies observations. And for our purpose, we used instruments from the millimeter, far infrared actually, to the millimeter and centimeter, and with the following instruments: IRAC, SPIRE, NIPS, PAX, and WISE. You can see here the website if you're more interested. And the data that you get is also in form of a FITS file, which makes it very useful for post-analysis using Python and for making post-analysis.
Like said, we wanted to pixel by pixel the set fitting of the data. But so it means that we want that the fluxes that we want to analyze must come from the same area of the galaxies and must relate to the same emission we are interested in. In this case, it's the dust emission. But the data set we are using comes from different instruments, which has different resolution, different pixel scales, etc. So we need first to homogenize the data. To do so, to overcome this problem, we use this HIP pipeline developed by Pantoni et al., which is able to subtract the emission of the background, mask the foreground stars, and also convolve the different images of different resolution to the same reference one, which in this case is the SPIRE 500 instrument one. And also regrids and reprojects the different images to the same frame. In this way, all the images have the same pixel scale and the same resolution. We also compute, in order to trace, to consider the propagation of the error of all these different steps, we compute a Monte Carlo error propagation analysis. Basically, before using the pipeline, we added to the original images a random normal distribution centered on 0 and with standard deviation equal to the original uncertainty on the map. And we repeated this process for a number of n iterations. So we end up with n iteration for every images, and we applied the pipeline for each of these iterations. And at the end, we end up with n process data for each filter. And we calculate the standard deviation from all these map. And in this case, we were able to calculate a pixel by pixel RMS map. In this way, we were able to take in account the uncertainty and the propagation of the intense uncertainty and the correlation of the different pixels of the maps.
This is an example. So we use the data from Spire, PAX, Spitzer, and that's PAX 70 with different resolution and different pixel size. And now we want to reproject everything to homogenize the data so that we can compare with the data with the worst resolution, which is Spire 500 micrometer. And this is the raw data before homogenization. And then we perform cropping and background subtraction. And then we convolve the data to the resolution of Spire 500 micrometer. And this is the final result after homogenization. And then we redo this over and over again using the original maps from Monte Carlo to see how error, the uncertainty propagates through these steps. And this one is another Galaxy NGC 1140, and this is the after image.
Okay, maybe it was not said before, but we spent most of the week trying to reproduce all these pipeline steps. But in the end, we, thanks to Lara, we realized we had some good reduced data to analyze. But after all this stuff, you maybe want still to check if you're doing things coherently. So we try to check whether some overlapping bands observation were matching a one-to-one relation. So as you can see, like in the high part, when you have high signal to noise ratio, there is almost a one-to-one relation. I'm saying almost because the bands are not perfectly the same, but I mean, it's good that we have that matching. But as you go to lower signal to noise ratio, you see that there's a deviation from a one-to-one relation and also a spread, which is due to, let's say, the random nature of noise. But also, as I said, a deviation, so a bending, and that is maybe due to some maybe sources that we cannot, uncataloged sources, or also some instrumental systematics. As you can see, there are some outliers in the bottom. But okay, in any case, what you're interested to analyze is your source, and hopefully it will lie on the upper right part of the plot.
Yes, so one thing, of course, is checking whether the signal is the same, but also the other thing is to check whether the signal to noise is more or less reasonable and also independent of each other, which is why we have done the Monte Carlo approach of then recalculating all the uncertainties of the images. So here I have two examples, one of the IRIC bands where I've then plotted the signal to noise ratio on the x-axis and then the number density of each pixel. And on the right is the Spire 500 micron that we have used to convolve all our images to. The idea is that the signal to noise ratio and therefore these histograms should more or less look the same before, which is here plotted in red, and after the entire reprocessing, which is here plotted in blue, so that we can actually use the images for the SED fitting. So on the left, just ignoring the extremely low signal to noise pixel ratios, which are the pixel to noise, the pixels in the background, where there's a slight difference. If you look at the high signal to noise ratios, which are the actual data that are in the galactic disk, which you want to fit, then the shapes are more or less the same. So in that sense, we are comfortable with using this for the fitting. And here we also see it for another PAX band.
This is an example of the This is an example of the SID fitting that we compute after the pipeline process. Basically, this is the data coming from that pixel of the galaxies, and on the right you can see like the comparison between the model and the data in the data set. We basically, for each pixel of the galaxy, we managed to calculate the physical properties of the source. We managed we find out that the radiation field decreases with radius of the galaxies, also the dust mass, and the pH fraction varies with dust mass. Thank you.
All right, questions for the wonderful dust map people?
Thank you. That was very interesting. The error propagation, I think maybe missed it. How do you define the distribution for the sampling for the MCMC propagation? Like there's a normal distribution, right?
Yeah, the Gaussian.
It's a normal Gaussian, yes.
What's the standard deviation? How do you?
For some data, there's a error map provided with the raw fits file.
Okay.
But for some data that the error map's not provided, the pipeline would just calculate the RMS of the background and then use that for error propagation.
Okay. Does it also account for like the instrument calibration errors?
Yes,
So
and
that's-
also in some filters, you can see the stars. So the pipeline would just mask the stars and also mask your galaxy so that you can calculate the RMS in the background as well.
Okay, very cool. Thank you.
Other questions? Group 6, you want to start coming down? So, well, I'll use while they're coming down a good question. So, what did you think in terms of the properties you extracted? So, what were the differences between the two galaxies that you thought were the most interesting?
Sadly, due to time constraints, we didn't manage to get all the S&D properties from both galaxies. But one thing that we can shortly show is that if we were to look at the average radiation field, that is more or less equally decreasing with radius. But then if we look at the dust masses per pixel, that even though it is decreasing with radius, there's also some smaller substructures within the disk. So at least it might be that at least these two properties are degenerate from each other, but there's also some differences than in actual how the dust is distributed within the disk relative to the average radiation in the pixels itself.
Thank you. All right, let's thank the crowd again.